We are on.
Okay, hi guys. I hope everyone can hear me, and that things are fine. Let me just add a comment. So I am Ariel Wolffe, and I will be hosting today's session. We are on day 4 of Developer Week. Yay. And today we have Louis Kinley, and he is doing today's session on microservices for sanity and savings. Hi, Louis.
Hi, how are you doing today?
Hey, I'm good, and you?
I'm doing great.
Awesome. So just so that I can give them a bit of background about you, so Louis hand-coded his first website in 1997 and most recently led engineering at an enterprise SaaS startup in Seattle, that's in the United States. And he relocated to Trinidad, where he's working with some Trini friends and an idea for the Caribbean. And so I'm pretty sure we'll be excited for that. And so today he's going to be looking at using the serverless framework to deploy microservices in AWS for rapid development and division of responsibilities, as well as reduced infrastructure cost. That is microservices for sanity savings. So, Louis, I would let you take it from here. You can go ahead and introduce. If you guys have any questions, feel free to add them in the comments, and Louis will answer them after or during. So you can go ahead, Louis.
Right, thank you for that introduction, Ariel. I'm going to go ahead and share my screen. Right, so microservices with serverless and AWS, staying sane and saving stacks. Stacks in all kinds of ways. A quick agenda just to give a rundown. I'll do a quick overview of monoliths versus microservices, just to make sure that everyone at least has some grounding in the differences and the advantages, as well as the disadvantages. I'll give a couple of recommendations based on my own experience with those things. And then pretty quickly, we'll dive into the serverless framework, some of the pieces in AWS that we'll be using that I've found most useful for this sort of thing, and then get into more of a live demo. I won't actually be doing any live coding because I'm not that brave, but it'll be close. So quick, as Ariel said, I'm originally from the Pacific Northwest, Seattle. I worked briefly on the team at Microsoft, left as soon as I realized that the corporate world wasn't quite for me. I most recently led a distributed engineering team for an enterprise data science company from Seattle, working with some of the Fortune 500, building a serverless processing queue for our data science, where we deployed dozens of serverless functions and various different communication techniques. I'm largely self-taught, but not without a lot of great mentorship, which has led me to really be an advocate for youth technology education and generally educating in general. So let's get to it. Monoliths versus microservices. We'll start out on the monolith side. A monolith is really just the idea of one single server running your entire application on every, a single instance that may be scaled horizontally or vertically to take care of the load, probably behind some sort of a load balancer or proxy. There's a lot of advantages. Deployments can be simpler. It's easier to deal with communication across your application. You can often just include a module or a service rather than having to drop a message in a bus. It's a lot of times easier to test and debug the entire application because you can run the whole thing locally and get much of the same behavior as you would in the deployed environment. You can take advantage of database connection pooling. You have a more consistent data layer because typically everything would be routed through the same data access. There's also no code duplication for cross-cutting concerns, things like logging, error handling, and what have you. There are also no cold starts. Your server is always running, so whenever somebody hits it, it's ready to respond. And that can really make a difference when you're looking at a 50 millisecond response time goal or something around that number. They're, of course, not without their disadvantages, too. Some of the disadvantages of a monolith are that the projects can get pretty large, right? After you start out, you build something, you know what you're building at first, but as the business needs evolve, customers are asking for different features, you start adding things on to your monolith because, well, it's the only server you've got. And it can be hard to tell exactly when the right time to start breaking things out is. So you may wind up with a bit of a mess. Scaling can get expensive depending on the resource needs of your server. You might be looking at hundreds of dollars a month for a single server. Multiple work streams, as you have multiple teams working on things, you might have people touching the same service, can lead to merge conflicts, decisions of whose work needs to go in first to make sure everything works, what gets deployed. There can be a little bit more management overhead there. Additionally, monolith can become a little bit fragile. Somebody can miss a single bug that, when found, might take down your whole server and mean all of your users are now without any service. There's also, again, the question of when to start breaking things out. When is the right time to create a new service or create a new server? What business logic, what features belong where? There's also a question of data segmentation and security. Maybe the messaging part of your application where users are sending messages back and forth or to your customer support doesn't really need to know about all of their account information or whatever data they're storing in your application. So it can be more challenging with a monolith to separate those concerns and control who has access to what. So let's take a look at microservices and plenty of cat pictures. One of the big advantages of a microservice architecture is that it's pretty easy to build new discrete features. There's really minimal downtime as you're deploying because your code is just running in a container. It's only executed when it's invoked. So you upload a new copy of your code. It's deployed to whatever platform is running your code. As soon as the next person hits it, it just pulls the new copy or the new container and runs the new code. It's pretty easy to manage your development across teams because you can break out a feature or a service and assign it to a given team. So there are typically fewer conflicts there. It's stateless by nature, so it really encourages developers to make the right choice. It's also easy and cost-effective to scale, right? There's paying per invocation. You're only getting charged for exactly what you use, and typically the rates are very cheap. In AWS, at least, the first 1 million invocations per month are free. Beyond that, it's fractions of a penny. It's easy to use a unique data source for a given feature, so not everything needs a relational database. Some things might be more appropriate with NoSQL type document store like MongoDB than a full Postgres database. With that, data security is also easier to manage for the most part, because you can really tightly control what service has access to what data. But with all these benefits, we are not without drawbacks. Sometimes a microservices architecture can feel a bit like herding cats. One of the biggest ones is that when you decouple your application like this, you have to get a little bit creative with how you're communicating sometimes, whether that's a queue, a message bus, or something else like an HTTP request. You have to add in that extra layer to enable your services to work together. Debugging and testing can also be a bit of a challenge, right? It's easy or simple to test a single service on its own or to unit test it, but to test the entire system means you have to have it all deployed, you have to know where to look, what to test, or have a complete suite of mock requests for every service. Cross-cutting concerns, again, your logging, your error handling, become a little bit more work, a little more overhead, because each service has to have some means of communicating with those things. Sure, you can include some of these as packages in each service, but at some point there's a central service that's dealing with these things. Your data models may be inconsistent. It just really requires a bit more planning and forethought. The flexibility that microservices offer in terms of language choice may also add complexity. While one team might love writing in Python or Java, a team of purely JavaScript developers might really struggle then to jump in and work on those services when needed. It can also lead to a little bit of a fiefdom mentality where some teams feel they have ownership over a given set of services, and it can cause friction on the team. At the same time, configuration and deployment across the entire system could be a challenge to orchestrate. When you have a dozen different services that all had to have one small change because of one of your central cross-cutting services being changed, you now have to figure out how to test and update all of your services at once. Further, if you have security requirements that really prescribe, specific VPCs or access to given services, the additional networking complexity of setting that stuff up with microservices can definitely add some DevOps overhead. So not without the drawbacks. In my experience, monoliths have really been great for starting new projects, getting something up and running quickly, because it's easy to see the whole picture. It's easy to spin up a Docker image to launch whatever your REST server or whatever server it is. Additionally, monoliths are really great for CRUD when data relationships matter and you need that relational database. You don't really want each microservice to understand the schema of every other service in the system, but when you're dealing with input output that needs to know the relationship between a user and the data that they're inserting, monoliths definitely offer better speed in access to a relational database. Now, on the other hand, microservices are great for asynchronous tasks. As you saw on Tuesday, I believe, with Erwin and the funky functions in Azure, doing asynchronous processing is something that these functions as a service really excel at. They're also great for high volume or when the data is kind of unrelated. For instance, a messaging system. If you just want your users to be able to send simple messages back and forth, maybe that just needs to live in a NoSQL database, and you don't really care, other than a user ID, what those relationships are. So enough about that. Let's get into how we actually apply these things, or how we can launch some of these things to suit our needs. I've chosen the serverless framework for a number of reasons. It's cloud provider independent. They have modules and templates for all the major providers, Amazon, Google, Microsoft, IBM, as well as a few others. They support local testing with some caveats, as well as being able to tail the logs from your functions that are deployed all from your local command line with pretty simple commands. Additionally, it's open source. It's NPM based, and as such, it has a very rich plugin ecosystem. Pretty much anything that you could want to do, whether it's setting up a domain name for your deployed HTTP endpoint, or pulling variables from another section of your serverless system that may not be in the service you're working on, it's all possible. The framework is also very well documented. In just a minute, I'll just jump on their page and flash through that a little bit. It's serverless.com. My favorite thing for those of you who have dealt with DevOps, sometimes when you're creating infrastructure in the cloud, figuring out all the connections that need to happen, making sure the right things point to each other and reference each other can be a little bit tedious. And serverless makes that pretty painless. It really provides a nice interface for creating those resources and making sure the connections are correct so everything works. Brief overview of some of the templates they provide. There's 32 listed here, and there are a lot more you can get via plugins. You'll notice a lot of these are AWS. I think they support about 8 or 9 different languages in AWS Lambda, and a number more in other providers. So because most of my experience has been in AWS, that's what I will be looking at today. We will be putting together a simple API gateway endpoint to trigger a Lambda function on a post request and store some data in a NoSQL database, which will then trigger another Lambda function based on that addition to our database. Now, in my experience, DynamoDB, which is AWS's in-house NoSQL database, very much like Mongo, has been really a great solution as both a document store and a queue. The ability to create a stream from your table and read items out in batches is really been great. There are other options for queuing, of course, but today we'll be looking at this one. So putting it together, it'll look something like this. So let me find the right screen to share. I guess first off, are there any questions? All right, no questions so far. So let's see.
I don't think we have any questions yet.
All right, let's see. All right, so if we share, right, so to get started, and I apologize for all the background noise if any of you are hearing that. Hopefully it'll end in just a few more minutes. So to get started, we need to install the serverless framework, which is a simple npm install. Right. Once we've got that, we simply tell serverless to create a new service for us using the template of AWS Node.js. I've already done that, so I canceled it, so it didn't overwrite what I have. But once that's run, it will give you something that looks like this. Right, can everybody see this okay? Right, so at the top here, it gives you the name of your service, and you can change this to whatever you want. Second, you'll see a whole lot of options about the provider you've chosen. Most important, of course, is the name and the runtime that you want your function to execute in. Further, there are packaging options, so you can include or exclude given directories or files to limit your upload. Then it gets down to defining the functions that you actually want to create. In this case, I've defined a function called add. I've told it that the handler to respond to events for this function is in the add.js file with a method called handler. I've named it, and you can see here they provide really nice interpolation. So you can reference things in this file. Self-service is simply referencing the service name at the top, and I've added the name of the function. We set the memory size. This in AWS goes from 128 megabytes all the way up to 3 gigabytes per function. Or timeout in seconds. For AWS Lambda, this ranges from 1 second to 5 minutes. And our event sources. What events do we want to trigger the execution of this function? Here I've told it we want an HTTP endpoint with a path of add and the method of post. So if we come to look at our add handler, when you run the SLS init or create command with the template, it creates a simple handler that looks a lot like this. So it's just a simple function with an event, a context, and a callback parameter. The event contains all the information that is sent or triggered by the event that's triggered this function. And the callback is what allows you to end the execution of this function with either a success or failure. So in order to access some other AWS services, we'll require or include their SDK. And to give us a little bit of nicety around checking the type of our input data, I've included the Lodash is plain object method. So it's best when you're setting these up to pretty much write all of your code in a try-catch block, because if you don't and your function errors for whatever reason, there's not necessarily going to be any logs about that or about why it failed. So in order to actually control the end of execution for this, here I'm just console erroring or logging this error and returning the callback with HTTP error response. So because we want this function to add a new record to our DynamoDB queue, we're using the AWS SDK to access DynamoDB, and they have a few ways of doing it which provide different drawbacks and benefits. The document client I've found to be the most pleasant to work with, as it generally accepts a whole JSON object as your input and doesn't complain too much. So next up, we need to actually parse the event that they're sending us. When The event comes in, there's a body property on it, which we're extracting here. We want to check if that's a plain object, if the request that's been sent to us was actually in JSON or if it was in text. If it's text, we want to try to JSON parse and get a usable object out of that. Next up, we need to set up the actual record or data that we want to input into our table. So we're just going to simply create a new record with the email, which has come in our request body, and a created on timestamp. Simple for now. You can expand this, of course, to however large you want, and it does a great job of supporting whatever data type you wanted to send. So if you wanted to send a property which was also an object or a map, it handles that, takes arrays. I'm not sure about functions, but that would be a strange use case anyway. So our document client for DynamoDB takes a couple params. It requires the item that you want to insert, as well as the table name of the table you want it to insert to. And there are others you can send, but these are the only two required. And the method on our document client to put the record is simply put. We send it our params and tell it we would like it to do this in a promise or using a promise rather than a callback. So once it's done that, we tell it that when it's been successful, we just want to set a success message and return ourselves the callback from the function handler or the event handler with no error and a success message. But if there's been an error in that execution, we'd like to catch it, log it, and return our callback with that error message. One of the caveats with using Lambda and API Gateway is that you have to create your own HTTP response bodies and objects. So there are only two required params. The status code, if you don't include this, you won't get any meaningful response back. In fact, you may not get any response at all, which can be a bit confusing and frustrating at times. As well, the body needs to be JSON stringified. They don't do that for you. So I've just created these simple methods to return either a 502 error or a 200 success with whatever message we've sent. And that pretty much fills out our initial handler. So let's hope. I think I got all of that. So let's go back to our terminal and see if we can deploy that. So if we come back here, we can simply type serverless, which they shorthand for you to SLS, deploy -s for the stage we want to deploy that, and we'll type demo. As it does this, it'll package up all our code, create, in this case, CloudFormation, which is AWS's native infrastructure as code language. So it creates that file for us, uploads it to wherever it needs to be uploaded. And actually, I forgot a couple things, so this may not work. Kill that before it kills itself. So let's go back to the serverless YAML file for a second and fill this out a little more. So one of the important sections I forgot is you need to define what region that you would actually like this to deploy to. This, I assume, is pretty standard across the board. The profile for the credentials that you have stored in your terminal environment. the default memory size for your functions, the timeout, as well as the stage that you want them deployed to. And you can see here, we've used interpolation to get the option passed in from the command line. We want the stage option. And here I'm defining an S3 bucket where I would like it to package and deploy all this code to. I think we also want to give our function some environment variables. And you can define these at the provider level, which makes them globally available for all your functions. Or you can include them at the same level as your events and all the information for each specific function if you would like to have more specific environment variables. Another piece in AWS are the IAM role statements, which really just define what resources this function is allowed to access. I'm sure Azure has much the same concept. And we're defining that at the provider level, which makes it global to all our functions. And again, we can take this block and make it specific to each individual function if we would like to be more granular with our control. So that's not going to work because, so let's keep filling this out. Quickly, I'll go through. So we're going to have to add another function to handle the stream from our DynamoDB table when things are added. This looks really similar, except for the events that we're using here. We're telling it that we would like it to take a stream from DynamoDB, and the resource name or identifier for that stream is going to be gotten from within this file in our resources block, where we define our DynamoDB table. These properties are all really just found in the AWS documentation for the given resource you're creating. The most important ones, of course, are the table name and the stream. You have to define your attributes and your key schema, and provisioning your throughput is 1 read per second or 1 write per second, although they measure that kind of interestingly. So 1 actually allows for at least 2 simultaneous read writes per second. And finally, if we want anything from this file to be accessible to other serverless functions, we can add some outputs down here at the bottom. It allows other stacks or functions to access this information. So that's complete. And if we now come back to try and deploy this, let's not deploy that just yet because that code's not there. Right. So if we deploy this now, it should all work happily. And as it's doing this, it will actually create the DynamoDB table function and an API gateway endpoint to serve that HTTP event that we asked for to take our post request. One thing that I've found very useful is to keep your packages as small as possible. When you start including a lot of different modules to do different things, this file can grow quickly. It's amazing how big node modules can be. And the smaller your file, of course, the faster it will upload. The first time you create a stack, you can see it's taking a little while because it's going through and creating all those resources for us. It usually pauses and then jumps forward. But on subsequent deployments, you can deploy a single function at once, which is almost instantaneous, depending on, again, the size of your zip file. Do we have any questions to this point? Ariel, are there any? I'm not hearing you.
Hey, so we have one question.
Yep.
So someone is asking, they are curious if you recommend this over Firebase or other alternatives.
Right. So Firebase, I haven't worked with a lot. From my limited knowledge, is really a backend as a service. And I would say it really depends on your use case. If you want to get something up and running quickly as a prototype or something that really doesn't have stringent data security requirements, it may well be simpler and faster to use Firebase. But if you're planning to build this as a part of a bigger architecture or bigger project, then keeping everything in the same cloud environment offers definitely some advantages. So it really, I guess, depends on your appetite for complexity and as well your resources available. And this is really taking its sweet time. Okay, so I've actually already got this deployed, so let's not keep waiting for that. So when we deploy, it'll give us something that looks like this, where it outputs all of the information about the endpoint it's created, as well as the function names you've created. So if we take this URL it gives us and bring it over to a request client, in this case I'm using Postman. So if we send that request, ideally we should see it just tell us that it successfully added the record. And if we come back to our terminal, we can now get the logs from that function, which I have a little excessive here because I wanted to see what was happening. And if we check the logs from a function we haven't written yet, it should show us that interesting. As you can see, the log output is not the nicest, but it at least doesn't force you to go into your console to find. So let's come back and look at what that next function to respond to our DynamoDB stream looks like. Let's see. Right, so we uncomment that. Let's, again, this is the same generic handler template. We, again, include the AWS SDK. We, again, use our try-catch block. The events that come out of DynamoDB can be a little bit messy, so we need to have some method for parsing those. I won't go into this in great detail. When you're using this, just console log out the event, and based on that data structure, this is the parsing I've come up with. It really generally, if there's one record, it will be an object. You will have records.dynamodb.newImage, and that will be whatever object was just added to your table. It can also be, if there were multiple records, they're a little bit ugly. They use interesting keys like S for string or M for map that you need to pull the value of. So that's the kind of parsing we're doing here, just taking for that given key, we want whatever value is stored here, whether that's S or otherwise. So once we've parsed those records, we can really do anything with them. I didn't write any code to show doing something with them because that's really up to you. But if this all worked, we should see. Let's see. We should get some logs out of it. Right. Sometimes they take, there's about a 30-second delay between when the logs from your function run actually get stored in this case, CloudWatch in AWS. But we can see here we got the original records. And this is an example of the object that came out of DynamoDB, where we have our event ID, the name, so it was an insert of a record. The source was DynamoDB, it gives us our region, comes down here, and our image that was actually added would be present in this object. And here's the example of the parsed record, where it's really just giving us this object that we just inserted from our post request. So this is what I found to be a very valuable set of tools in terms of creating a data processing pipeline, creating services that handle discrete bits of functionality, and really keep your costs low. You don't need to spin up large servers to actually run things or process things. If you have a large JVM, 3 GB of memory is probably enough to run it, and hopefully you can get it to execute in under 5 minutes. So even pretty heavy workloads can be handled in Lambda. They do charge per megabyte second, so you'll have to look at their pricing to really determine what those costs are going to be, but it's generally a small fraction of what you would pay with a full server. And that pretty much concludes my talk. Hopefully it's been useful and provides a little bit of insight into how easy it is to use the serverless framework to set up some of these resources and link them together to process whatever it is you need to do. Are there any more questions as we've gone through that?
Okay, so I'm monitoring to see if we got any more questions coming in. Awesome talk, man.
Thank you very much. Right. I can make this code all available, but realistically, this is all pretty much from the serverless documentation. And I think everyone listening is probably capable enough to find all this stuff and recreate it at their leisure. So thank you all for listening, and thank you, Ariel, for moderating. There's been some great talks so far during this Caribbean Developer Week, and I'm really looking forward to getting together with everyone on Saturday.
Hey.
Yep.
Okay. So we have one comment from Marcus. Marcus says, hey, this was pretty cool.
Thank you.
Yeah, I think it was pretty awesome. So, I don't know if you have any more comments, anything that you wanna add, as we have some spare minutes. If you guys have any questions, you can go ahead before we wrap up. If not, we'll.
Well, I guess I can also add a little bit for those of you who have more stringent data security requirements in your deployments, where maybe your functions need to access a database that's in a VPC that is maybe not publicly available to the internet. Serverless makes it pretty easy to run your functions in that VPC. Here you can simply add a VPC block. You give it the security groups and subnets that you want it to live in, and it hooks everything up for you. Let's see, what else is there? There's the ability to put this on a per function basis, makes it pretty powerful. The ability to cross-reference other serverless files or outputs is pretty nice. There's really a lot you can do. I would say it's not quite as powerful as something like Terraform in terms of total infrastructure, but with regard to a serverless architecture, this framework pretty much does everything you could think of. And with that, I think I've said pretty much everything I have. So I hope everyone enjoys the rest of the talks today and the rest of the week. And I'll see you later.
Great. Yes, thank you so much for this very, very informative session. And guys, coming up at 1:30, we have another session with Anil Ramnanan. And he's going to do a bit about a little introduction on machine learning and computer vision. So that's going to be exciting also. We have some pretty cool sessions. So yeah, thank you so much, Louis. And we welcome you into the community here. So enjoy. All right, guys. Thank you so much.